Hi everyone, good morning. Welcome. I'm delighted to welcome you to the CAE Fall 2025 seminar titled Transforming Wastewater into Resources, Innovative Technologies for Water Reuse and Nutrient Recovery. Our speaker is Dr. Qiufeng Lin, who is a postdoc working under the supervision of Dr. Esperandiroglu. She earned her PhD in Environmental Science and Management from Montclair State University in New Jersey in 2024. Before that, she got an MS in Civil Engineering from Zhejiang University in China and a BS in Environmental Engineering from Beijing Forestry University, China. Her research interests focus on advancing innovative water treatment and water use technologies to address water pollution challenges and to enhance water supply resilience in response to climate change. Thank you very much for doing this, and it's all yours.
Thank you so much, Dr. Pomnoy, for the kind introduction. Today, I'm honored and excited to share part of my dissertation work as well as my current postdoctoral research on the water and nutrient management. And today, my presentation is titled Transforming Wastewater into Resources, Innovative Technology for Water Reuse and Nutrient Recovery. To begin, I will provide a brief introduction to this topic. Whereas we know that about 90–70% of the Earth's water is salt water, leaving only 3% as the fresh water, in which agricultural sector will consume about roughly 70% of the global fresh water. With the population growth and climate change, our global water stress is expected to increase significantly. The increasing pressure on the limited freshwater resources highlights the urgent need for water reuse as a sustainable solution to meet the current and future water demand. In the United States, the most irrigation waters still heavily relied on the surface water and the groundwater, with the reclaimed wastewater accounting for less than 1%. And currently, about 80% of the U.S. population relied on the centralized wastewater treatment plant. Meanwhile, the remaining about 20% of the people relied on the decentralized wastewater treatment system, such as the Sabitan. Using the centralized municipal wastewater as an example, currently there are over 60,000 wastewater treatment plants across the United States, yet only 7% of the wastewater is being reused. This situation highlights that there is still very huge potential for us to expand the wastewater reuse in the future. Beyond the water, nutrients are also very important for agriculture. And let's look at this figure. This figure shows the global fertilizer demand from 1990 to 2022. And you can see that the demand has gradually increased over the time. And the United States is one of the major fertilizer consumer, accounting for about 11% of the global consumption, in which 58% of the nitrogen, 23% of the phosphorus, while 19% of the potassium. Now, it's very important to consider how these nutrients are produced. Where the nitrogen fertilizer is primarily produced by the Haber-Bosch process, in which the nitrogen gas from the air can react with the hydrogen under very high temperature, high pressure to produce the ammonia. Where this process is highly energy intensive and it will consuming about 2% of the global energy supply while contributing to 3% of the global carbon dioxide emission. In terms of the phosphorus, is sourced from the phosphate rock. This is a finite resources with the limited reserve. On the contrary, the potassium supply are more readily available from abandoned potash deposit. So given this constraint, current study are more primary focus on the nitrogen and phosphorus recovery as part of sustainable wastewater management. So After applying the nitrogen and phosphor fertilizer, where do these nutrients go? About 30 to 50% is absorbed by the crop, while the rest of them is lost as the agricultural runoff or enter our food chain. Eventually, it will appear in our wastewater system. So without the potable management, this nutrient-rich runoff and wastewater can enter our surface water system, leading to eutrophication issue and threaten our aquatic ecosystem. So we are thinking, if we can recover the nutrient from wastewater or reusing the treated wastewater, our reliance on the synthetic fertilizers and limited freshwater resources can be reduced, thereby decreasing the environmental pollution and improve the water quality. Eventually, this will create a closed, sustainable route from wastewater to food production. Although there are many advanced water reclamation technology, they often face the technical and economical challenges. For example, high-pressure membrane technology. They are super energy intensive and prone to the fouling issue, and it can generate the toxic constraint. For the advanced oxidation process, although they are effective at removing the trace organics, but their non-selective nutrient, which can reduce the overall treatment efficiency. That is because a large proportion of the free radical, it can be consumed by the coexisting water matrix. In terms of the ozonization, it suffers from the low solubility, high cost, and the safety concern, including formation of the harmful disinfection byproducts such as the bromine. Regarding the activated carbon, it's very difficult and expensive to regenerate. And in terms of the engineered natural systems, such as the constructed weather, it often requires large land area, and it has the variable performance depending on the season. Similarly, the nutrient recovery technology also fixes the significant limitation. For example, the stratified precipitation, it requires the significant chemical input and precise the pH control, while the biological recovery method, though cost-effective, it needs large environmental footprint, and they are very sensitive to the climate and operational condition. For ion exchange, it require frequent resin regeneration, and regarding the stripping and absorption method, it is very also energy intensive, and it often needs additional pH adjustment. And additionally, the aforementioned the method often recovery only the nitrogen and phosphor separately, which can reduce the overall treatment efficiency, and it will need multiple treatment systems. So the aforementioned challenge highlights the urgent demand for us to create innovative and cost-effective solution for more sustainable water reuse and nutrient recovery. And to address this knowledge gap, I will first introduce an innovative approach, ferret-enabled water reuse for agricultural irrigation, where the application of the ferret to water treatment started in the 1970s, and the ferret is an oxyanion containing iron in the oxidation state of 6 with a reduction potential of 2.2 volt. And it typically appears as the dark purple or violet solid that is highly soluble in our water. And generally speaking, the ferret is a very highly complex system. That is because once the ferret is dosed into our water system, multiple reactions will occur at the same time. And the unique properties of the ferret that are a treatment of the multiple treatment mechanism, such as the oxidation, disinfection, coagulation, absorption, precipitation. Little formation of non-disinfection byproduct acts well as the non-toxic final product makes the very promising wastewater reclamation technology. Although numbers of the study have proven the ability of the ferry to remove a wide range of the contaminant from drinking water, wastewater, groundwater, its potential for agricultural water reuse remains limited. Therefore, in this study, the overall objective is to conduct a comprehensive evaluation of the treatment performance and the underlying mechanism for ferry-based water reclamation. And in this study, the secondary effluent, that is the biological treated municipal wastewater, will be collected from a local wastewater treatment plant in New Jersey. And after that, we will treat with the ferry treatment under controlled laboratory condition. After treatment, sample will be analyzed for the key water quality parameter to assess their suitability for agricultural reuse. And in this study, the batch scale study will be carried out first to investigate the behavior of key nutrients under ferry treatment, and second to explore the degradation of a representative emerging contaminant in wastewater, and third is to evaluate the disinfection performance as well as the formation potential of the disinfection byproduct, and finally we will examine the effect of the ferry treated wastewater on the seed germination and seedling growth. And now I would like to share some of our experimental results with a special focus on the nitrogen. But before diving into the result, it's very important to understand the nitrogen forms typically present in secondary wastewater effluent. And generally, the total dissolved nitrogen consists of the dissolved inorganic nitrogen and dissolved organic nitrogen. Dissolved inorganic nitrogen containing the nitrate nitrogen, ammonia nitrogen, and nitrite nitrogen. Of note, the nitrate and ammonia nitrogen are only two nitrogen forms that the crop plant can directly take up, making them critical, important for evaluating the nutrient recovery and the water reuse for agriculture. And next, the key findings of the very mediated the nitrogen transformation is present, where this figure shows the different nitrogen species during ferry treatment of the secondary effluent, where let's look at figure A, we can see poor removal of the total nitrogen can be seen, indicating that the ferry have a limited capacity in total nitrogen removal. However, nitrogen retention in our wastewater benefits for agriculture irrigation. And moreover, with the increase of the ferry dose, dissolved organic nitrogen decrease accomplished by dissolved inorganic nitrogen increase. And to review the deep insight into the nitrogen transformation, we construct a relationship with the change of the dissolved organic nitrogen and change of the dissolved organic nitrogen. Clearly, they showed in a relationship with a slope equals to minus 0.97, which means that the loss of the organic nitrogen was primarily transformed into the inorganic nitrogen. But there are about 3% of the dissolved organic nitrogen was lost. And furthermore, we can find this straight fitting line had an intercept here. And the loss of the nitrogen might be attributed to the formation of the gaseous nitrogen species or certain volatile nitrogen containing organic species was produced from this system, and eventually it will escape from this system. And let's move to more detail in organic nitrogen species in the figure C, and they show different behavior. As we can see, with the increase of the ferry dose, nitrate nitrogen gradually increase. Ammonia nitrogen remain constant, while the nitrite nitrogen slightly decreased. And to evaluate the impact of the ferric oxidation on the distribution of the nitrogen species, this figure shows the fraction in different nitrogen forms before and after ferric treatment of the secondary effluent. Clearly, we can look at that the total nitrogen do not significantly reduce, but the ferric treatment can alter the distributions of the dissolved organic nitrogen, nitrate nitrogen, nitrite nitrogen, while remain the ammonia nitrogen. And more specifically, we can find the dissolved organic nitrogen decrease from 41% to 70%, while the nitrate nitrogen increased from 28% to 51%. We can find the increase of the nitrate nitrogen 2023 closely match the decrease in the dissolved organic nitrogen fraction 24, which means that the increasement of the nitrate nitrogen was primarily due to the dissolved organic nitrogen reduction. However, attention should be paid to the ferric-induced nitrogen leachability in the soil. That is because the ferric promotes a higher proportion of the nitrate nitrogen. Nitrate nitrogen is negatively charged. Meanwhile, our soil particle is also negatively charged, which can lead to the increased nitrogen leachability, especially in the sandy soil. And next, we will further explore the mechanism behind the dissolved organic nitrogen to nitrate transformation. Very interestingly, the nitrate is not a common reported as the final product of the ferric oxidation for many nitrogen-containing emergent contaminants. However, some recent studies have reported that there are certain wastewater constituents, such as the ammonia, it can activate the ferric to generate more reactive ammonium ferroporphyryl complexes to enhance the removal of the pharmaceutical. So building on this, we hypothesis that the ammonia in our secondary wastewater sample can similarly activate the ferric to generate more reactive complexes, thereby improving the dissolved organic nitrogen degradation. So to validate this hypothesis, we have investigated the effects of the ammonia on the dissolved organic nitrogen removal during ferric treatment. And our results show that the residual dissolved organic nitrogen decreased from 68% to 29%. Highlighting the role of the ammonia in enhancing the ferric-driven dissolved organic nitrogen removal. Well, let's move to the phosphorus. This figure shows the effect of the ferric dose on the change in different phosphorus species and the ferric utilization efficiency after ferric treatment of the secondary effluent. And as we can know that the concentration of the dissolved inorganic phosphorus from this secondary effluent was below the typical level. That is because the municipal wastewater treatment plant in New Jersey are required to mitigate the phosphorus before it discharges into our surface water system. And in a study, we can find that the ferric could mitigate the total phosphorus, including the organic phosphorus and inorganic phosphorus to different degree. And in terms of the artificiation efficiency of the ferric in 3 different types of the phosphorus species, they all share a similar pattern. Unfortunately, the phosphorus will be effectively removed by the ferric treatment. However, the ferric provides an alternative solution to organic phosphorus mitigation in the water because our traditional treatment process, such as the coagulation, is very hard to mitigate the organic phosphorus friction. And to further investigate the treatment mechanism of the phosphor removal, the size distribution of different phosphor species and residual ion was studied. In the study, the particle size between 0.1 to 0.45 milliliter, we can consider it as the colloidal particle, while the particle size between 300,000 Dalton to 0.1 milliliter, we can refer it as the narrow size particle. While the chemical species passing through the 300,000 Dalton's membrane, we can refer it as the soluble substance. As we can see, the removal of the colloidal and the narrow size total phosphor was primarily attributed to the mitigation of the organic phosphors, and they can be absorbed or incorporated into with the ferric-induced resultant particle. And moreover, a majority of the phosphor was truly dissolved in our secondary effluent sample, and soluble phosphor could gradually decrease with the ferric dose increase, indicating that part of the soluble phosphorus can be removed by the ferric oxidation. And additionally, the residual ion remain low concentration level at any ferric doses, regardless of the particle size range. This suggests that the dose ferric can be removed through the formation of the large size iron oxide or iron hydroxide particle, and finally be removed by the subsequent filtration process. Well, let's look at this figure. This figure shows the general patterns of the wastewater primary nutrient with the ferric dose, and the ferric is sourced from the potassium ferric. So as the ferric dose increase, potassium gradually accumulates. Nitrogen remain constant, while the nitrogen significantly decline. Next, to better quantify the safe fertilizer by reusing the wastewater nutrient, the fractions of the wastewater nutrient supply in annual nutrient needs are estimated for the 4 crops that are cotton, sugarcane, corn, and wheat. They are commonly grown in Florida. We can easily to find that the potassium retained in our wastewater sample can 100% to provide the enough potassium required for the growth of the 4 selected crops. In terms of the nitrogen, although the reclaimed water cannot cover the overall nitrogen needs for the 4 selected crops, the use of the nitrogen fertilizer can be saved by 70% to 60%. In terms of the phosphor, the residual phosphorus in the ferric-treated wastewater can only provide a mirror fraction, suggesting that the substantial phosphorus fertilization is still required for the crop irrigated with the ferric-treated wastewater. And next, we evaluate the effects of the ferric dose on the degradation of representative emerging contaminants commonly identified in the secondary effluent. We can find as the ferric dose increase, the residual XMX concentration significantly decline, and remarkably, a ferric dose of the 7 ppm is sufficient to remove over 96% of the emerging contaminants under the neutral pH condition. Actually, the ability of the ferric to as a powerful oxidant to remove virus wastewater derived emerging contaminant has been widely reported. And this capacity is very important for enhancing the safe and quality of the reclaimed water for agriculture irrigation. Next, we also examine the disinfection performance and its impacts on the disinfection formation potential, because both of the micro-contamination and disinfection byproduct in our reclaimed wastewater can pose the healthy risks to the cropland, and as well as the farmer workers. So this figure shows the log reduction of the total coliform and E. coli at different ferric doses. Although the ferric could effectively inactivate the bacterial indicator, the treated effluent still could not meet the EPA water reuse guidelines, even at the ferric dose of the 9 ppm, suggests that a secondary disinfection process is still required to distribute and store the ferric-treated wastewater before reuse. And here, this figure shows the formation potential of different disinfection products after ferric treatment. As we can see, the ferric can elevate the precursors of the THMS, 11-DCP, and HANS to different degrees. And finally, to assess their agricultural impacts, we cooperated with the soil and plant experts from University of Florida to test the corn seed germination and the growth. And let's look at this table. It shows the effects of different irrigation water on 7 days seed germination. We can find, compared with the DI water, untreated wastewater show improved germination index, where our ferric-treated wastewater showed improved germination performance, indicating higher and faster germination. And this figure presents the effects of the different irrigation water on seedling height and fresh biomass. We can find the ferric-treated water support the healthy seedling growth performing as well as and even better than the DI water, where the untreated wastewater will hinder the plant's growth. So quickly to summarize this section, ferric treatment for water reuse offer multiple benefits. First, it can increase the potassium while retaining the nitrogen concentration level in wastewater, but it will effectively remove the phosphorus, including both the organic and inorganic forms. And third, it can elevate the emerging contaminants in wastewater and reduce the precursor to different disinfection byproducts. Most importantly, when we test the treated water for irrigation, it will promote the corn seed germination and the growth. Overall, the formation result demonstrate that the ferric is a promising technology for safe and sustainable agricultural water reuse. And next, I would like to introduce another innovative solution called the electro-hydromodulation for nutrient recovery. And this is an ongoing project for my postdoctoral study. So what is EHM? This is a chemical-free electrochemical pH modulation process to simultaneously recover the nitrogen and phosphorus from municipal wastewater. Unlike the traditional electrochemical method that use the superficial anode to release the cation, like the magnesium ion, leading to the anode consumption and the metal accumulation. Instead, we employ the inner graphic coupling with the multivalent cation exchange membrane, where this design offers 3 key benefits. First, it can extend the electrode lifespan and improve the cost effectiveness of the superficial system. Second, it enables the chemical-free pH control. For example, in the anode 1 section, we can find the water oxidation can produce the hydrogen ion where the pH will be decreased, and it can drive the cation across the membrane to the cathode section, while in the cathode section, the water reduction will produce the hydroxide ion, where the pH will be increased to promote the nutrient precipitation. And finally, our treated wastewater go back to the second anode section for pH neutralization before it discharge. And third, the modular membrane stacks are more easier to scale up. So in this study, the primary goal is to demonstrate the feasibility and treatment performance of the EHM system for both the nitrogen and phosphorus recovery from municipal wastewater. And to achieve this goal, we will firstly evaluate the EHM nutrient recovery efficiency via the lab scale setup, and then use those insights to design and deploy a field scale system, where this diagram shows a batch scale continuous for nutrient recovery process. And firstly, our municipal wastewater will go into our NO1, where pH will be decreased, and then treated wastewater go back to the cathode section, raising the pH, and then it will move our water into a phosphorus precipitation tank, and here the phosphorus will be recovered as the calcium phosphate. And then after passing through a filtration unit, the phosphorus-free water will go into ammonia stripping column to strip the ammonia. And the ammonia here will release as ammonia gas, and then it will absorb in absorption column. Ammonium here will recover as the ammonium sulfate. And finally, the nutrient-free water will go back to the NO2 section for pH neutralization before it discharge. Next, let's review some key findings of our study, where this table shows the water quality data for municipal primary effluent at Florida wastewater treatment plant. We can find the total phosphorus and total nitrogen. Their concentration are 3.25 and 42.3 milligram per liter respectively, of which 59% of the total nitrogen is present as the ammonia nitrogen, while the 94% of the total phosphorus is appear as the orthorophosphate. And let's look at this figure. This figure shows the pH profile and nutrient recovery performance by the lab scale EHM treatment of the municipal primary effluent. The y-axis on the left show the pH profile, and the right y-axis show the concentration ratio. And after 4 hours of the treatment, we can find EHM treatment achieved 93% of the ammonia nitrogen recovery, as well as 98% recovery of the orthorophosphate. Additionally, our pH profile indicates a very clear trend. The pH will be decreased in the NO1 and then increase in the cathode section, and finally to be neutralized in a second anode section. Furthermore, we also test a different type of the wastewater using the similar process, and our EHM system achieve over 90% recovery of both the ammonia and orthorophosphate. So, encouraged by this lab scale outcome, we have advanced to a field scale EHM pilot for the nutrient recovery. And right now, this system is located in a single family house in Palmetto Bay. And this system is housed in a 8 by 10 feet shed. It can trip up 300 gallons of the wastewater per day with a typical flow around 200 gallons based on our yearly household monitoring. And we have also installed a dedicated electrometer to check the energy use, will help us to calculate the energy demand for recovering the nitrogen and phosphorus from our system. And this system is connected to the home's Sabitan. And recently, we have tested the water quality of the raw Sabitan effluent. The results show that the effluent has a near neutral pH with relatively high of the conductivity and turbidity. And the chemical oxidation demand reached around 175 milligram per liter, suggesting a very high substantial organic load. And when we look at the nutrient, total dissolved nitrogen is quite high, around the 135 milligram per liter, with most of the nitrogen appear as the ammonia nitrogen. And in terms of the total dissolved nitrogen, its concentration also reached the 15 milligram per liter. And this finding confirmed that the Sabitan effluent contains high levels of the recovery nutrient, making it as an ideal source for testing our EHM nutrient recovery system. And actually, this project has real-world impact because it not only recovers the valuable fertilizer from wastewater, but also helps mitigate the Sabitan system failures caused by the climate change impacts, such as the sea level rise and coastal flooding issues. Where this figure shows the process flow of our EHM pilot plan, highlighting some improvement over our lab scale setup. And firstly, the Sabitan influent will goes into the NO1, where the pH will be decreased. And then we have add a CO2 stripper here. The function here is to remove the dissolved carbon dioxide. And it can also reduce the water buffering capacity, cause the pH to increase before the water flows into our cathode section. And in the cathode section, the pH continues to increase, which benefits the subsequent nutrient recovery process. And then the water moves into the phosphor precipitation tank, where calcium phosphate sludge will be formed, and excess sludge will be pumped into a phosphorus fertilizer collection tank, while excess water will go back to the phosphor precipitation tank. After phosphorus-free water is filtered by a filtration unit, and after filtration, the water will goes into ammonia stripping column, where the ammonia here will be released as the ammonia gas and captured in the adsorption column with the sulfate exit. So here the ammonia will be recovered as the ammonia sulfide. And finally, the nutrient-free water will go back to the second anode section for pH neutralization before it discharges into our leaching field. And the photo on the right shows the actual pilot installation. And right now, we have complete all the wiring and connected all the tanks to our control panel to achieve automatically operation. And our next step is to stabilize the system and begin monitoring the performance under different water quality conditions. And we are also excited to share more results as this project progress. And in this project, the core innovative component actually is the EHM reactor. But scaling up from lab scale to field scale is not just the enlargement. We should consider a lot of factors such as the hydrodynamic, current distribution, durability, and the cost. So to tackle these challenges, we have engineered a modular EHM cell stack, and this figure shows the schematic of each cell scale modular. And each module, it contains 4 cathode, 4 anode, and 5 graphite electrodes calibrated by 4 multivalent cation exchange membrane. And each cell is connected through a flexible inlet-outlet system, allowing adaptable flow configuration. And picture on the right, it shows the successful assembly process from the graphite membrane and to the complete cell stack with all tubing connection. So in the summary, our lab scale tests have confirmed the EHM process can recover over 90% of the nitrogen and phosphorus from municipal wastewater. A standout feature is that it's chemical-free pH modulation, enabling the phosphorus precipitation and ammonia absorption. And moving forward, we will focus on 3 directions. First, we will validate the long-term stability, scalability, and energy efficiency of the system under viable conditions. Second, we will assess the economic value of the recovered fertilizer product. And finally, if this project is successful, we will pursue the regulatory integration through ICC standard 825. This is the international code for the primary sewage disposal system. Aligning with this standard, it could ensure our system meets the requirement for safe and sustainable and climate resilient decentralized wastewater treatment. And lastly, I would like to highlight the environmental implication. These 2 projects have profound and transformative implication with a focus on the 2 key areas. And first, they advance both ferry and EHM science and technology through efficient recovery and reuse the nutrient from wastewater. Second, these 2 projects foster the long-term resilience and sustainability of the U.S. agriculture. First, they enhance the water quality and protect the public health. Ferry effectively remove a wide range of the contaminants, providing clean and nutrient-rich water for irrigation. Meanwhile, our EHM system recovers the nutrient from wastewater and minimizes the pollution to the surrounding water body. And second, they secure a sustainable nutrient supply through recovery and recycling the nutrient from wastewater, reducing our dependence on the commercial fertilizer. Third, they strengthen the agricultural resilience and sustainability, particularly in water-stressed regions, by reusing the ferry-treated wastewater for irrigation and EHM recovered fertilizer. It can reduce our reliance on the limited freshwater and the synthetic fertilizer while supporting the cropland productivity. And fourth, wastewater reuse and nutrient recovery will preserve our natural resources and protect our environmental quality. And lastly, the aforementioned this benefit will increase our willingness of the stakeholders to apply the wastewater reclamation and nutrient recovery technology, thereby improve their market acceptance, and eventually it will have a profound social impact. And at the end of my presentation, I would like to take a moment to express my sincere gratitude, and special thanks goes to my postdoc supervisor, Dr. Expert Andilo Group, as well as my PhD advisor, Dr. Yang Deng, for their invaluable guidance and support through this project. And also, I would like to also thank the University of Miami, Montclair State University, and all our funding agencies for providing the resources and opportunities to make this two study possible. Thank you so much.